So on the test, I will provide this whole backside to you in some way, shape, or form. The front needs to be memorized.
What does that mean? Like in some, like it's not going to.
Like I'm gonna hand you a card. It might just be printed on the test somewhere.
Yeah. Okay.
Yeah. Okay. So either way, no matter where it is on the test, whether it's a card or whether it's on there, we know that we're adding or subtracting an angle. Well, it looks like we're subtracting sine, so we should go towards this guy. That once I figure out my A and B value, it's just sine of A cosine B minus cosine A sine of B. So I go back here and I'm like, oh, you know what? My first angle is always kind of my A value. My second one's my B value. And all that negative does, it tells me what identity to use. So I won't throw that negative into those angles. So I have 45 and 120 and that's it. So this is going to equal sine of 45 degrees. Cosine of 120, did I say? Yeah. And for sine, when you subtract angles, you throw a subtraction in there, and then we just flip the cosine and sine. So we have cosine of 45 and sine of 120. Sine of 45, square root of 2 over 2. Cosine of 120, we should know it's negative because we're in quadrant 2. And we might have looked this up, but it's negative 1/2. It's okay if we look it up as long as we know how to read the unit circle. Cosine of 45, square root of 2 over 2 times square root of 3 over 2. I am going to note I have a negative and a negative. There's only one up there that has two negatives in it.
C.
So I don't even need to simplify it. I could just put C down.
I know what I did wrong.
So we're going to have a negative square root of 2 over, we multiply our denominators to make 4.
Oh my gosh.
Yeah.
Minus square root of 2 times square root of 2 is square root of 6 over 2 times 2, which is 4, which equals negative square root of 2 minus square root of 6 all over 4.
I just would have added them, I guess. Honestly, that's what I was going to guess.
The wrong letter.
Okay.
Okay.
He's appealing.
No,
Wait, Mr. Pabian, when is it?
Remember, I just walked around to see if you guys had the proper work. If you had the proper work, you're probably fine.
Okay.
If you add them, will it be like something root 3? Like, when will there be a number outside of the square root?
Oh, there'll be something outside the square root if you'd have something outside the square root. Or if you're adding or subtracting square roots. So if I have like square root of 2 plus square root of 2. If I have a square root of 2 and I give you another square root of 2, you have 2 square root of 2s. So whenever you add. Or it could be a subtraction, like maybe I'm thinking a negative square root of 2 minus the square root of 2. That would equal a negative 2 square root of 2. You can always think of square roots as being x's or y's. So as long as they're the same, if I had x plus x, I'd make it 2x. Can we ever do x plus y equals 2xy? Here's what I'm looking at. So we can do x plus x equals 2x, right?
Yes.
But if I have x plus y, can we do anything with that? No. This is why we can do square root of 2 plus square root of 2 equals 2 square root of 2, but we cannot do square root of 2 plus square root of 3. It's basically doing x plus y. They're different things, and you can't add them. A little bit of a tangent, but it's good to know those algebra facts. Go.
I just saw this. It was a positive sign 75, and then I just took the negative and answered that. Does that count as like work?
Well, I saw your work right there.
Yeah.
Yeah. You actually did the work. I'd prefer this work versus just knowing it's the opposite. Yeah. Okay. Questions about work? And I'm to assume there's no questions on the homework, so we can just roll right into. I just said there's no questions on the. I'm just kidding. Kate, I saw your hand.
You just go through like number 11.
Sure. Am I on the wrong one?
No, that's right.
Oh, okay. Oh, number 11. We're just adding those two things together, right?
Common denominator.
Just common denominator. So I just wanted to get across the fact that whenever we need to push two fractions together, we just multiply by the other denominator. So this is just asking you to take the 3 pi over 4 and multiply the top and bottom by 3, because I borrowed that other denominator. And then we're going to go ahead and we're going to add pi over 3. And we multiply by the other denominator, which is 4. And so this would give us 9 pi over 12 plus 4 pi over 12. Now we can add them because they have the common denominator, which would give us 13 pi over 12. Yeah, it gets confusing when I... Yep, because I put it in like a confusing section, and you're just like, okay, it's got to be just as hard as the rest of the stuff. One sign is I didn't give you much space to do it in, so it can't be too hard. All right, other questions? 17. Wait. Oh, so that's 17, right? Okay. You got to do something. Guys, on the test, you have to do something. Don't leave anything blank. So if you're out of things to do, just turn things to sine and cosine. So if I'm looking at this one, I can turn that tangent into sine over cosine. So if I'm completely out of things to do, I'm just like, oh, you know what? I'll have cosine x over, instead of tangent, I'll change that to sine x over cosine x plus sine x. And now I kind of have my two sides. Okay, now I can at least do keep, change, flip. I should be able to reduce something like that. Either keep, change, flip, or realize you can multiply the top and bottom by cosine. I like the multiplying top and bottom by cosine because I don't have to do a lot of side work. So once again, if I multiply the top by cosine and bottom by cosine, I'll cross those out and I'm left with sine x. I don't think I've done keep, change, flip for a while, so I'm going to go ahead. I'm going to use keep, change, flip on this one. So if I was to use keep, change, flip on this, I'd have cosine x. I'll turn that into over 1 times, flip the bottom one, cosine x over sine x. Well, that's just cosine squared over sine x plus sine x. Didn't get me very far. Kind of looks pretty much the same. What's something we need to learn how to do effectively, I should say? There should be something that stands out to you. If you've been practicing on all of these, the squared. So I'm looking for maybe a sine squared.
Yeah.
So that's a good thing to pick out. I'm looking for a sine. I have a sine, but I don't have a sine squared. And second of all, can I just add these as is?
No. Find a common denominator.
I need to find a common denominator, which means I'm going to multiply both equations by the other denominator. So remember, we actually have sine over 1 here. So if I multiply by the other denominator, I would take that 1 and multiply the top and bottom by 1. Does that change anything in the other fraction? No. So my other fraction is still just cosine squared x over sine x. Now I'm going to take that sine x, multiply the top and bottom of this fraction, which we suddenly now have sine times sine, which would be sine squared x, all over sine times 1, which would be sine x. Can I push those fractions together now? Yes, because they have a common denominator. So now we just add the numerators, and look at what we have. We suddenly have cosine squared x plus sine squared x all over sine x. What's cosine squared plus sine squared? 1. So all of this is just 1. What's 1 over sine? Cosecant. So we have cosecant x. And then on the other side, I have that cosecant x as well. So we're got it. But please, 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 on the test, do something. Don't make up rules either. Just do something. Even if it's just changing everything to sine and cosine. Even if it's not the right thing to do something. Don't leave it blank. Because sometimes just doing one small thing, even though you have no idea what's going on, that one small thing might be that thing that tips you off and goes, oh, this is the type where I have to push it together. And that's what I should have noticed in the beginning, that these are two statements, turn them into one. The only way I can do that is I can push them together somehow. All right, other questions? Go. 9. So no? Who wants to know that number 9 is wrong on the answer key?
I knew it.
I want to do it.
Should have emailed me. You want to? All right. Can someone help me out and tell me how I can add two angles together to equal 5 pi over 12? How do I make 5 pi over 12 with angles I know? And you can take a shot. You can guess. I'm going to check it anyway. Pi over 6 plus pi over 4? And if you're not sure of this, I'll check it off to the top right. I'll say pi over 6 equals 2 pi over 12. And pi over 4 equals 3 pi over 12. 3 pi plus 2 pi, 5 pi. We have it correct. This is the most difficult problem on these homeworks, so I'd pay attention to this. It is the most difficult because what is the tangent of pi over 6? Square root of 3 over 3, which is probably the hardest one to deal with in tangent land. Because let's look at what this is going to do. We'll see what this turns into. All right, so if you look at your identity sheet, if you're adding an angle for tangent, it turns into tangent plus tangent all over 1 minus tangent tangent. So that sounds weird. All right, so we're going to have tangent of pi over 6. Don't write big if you're following me. Plus tangent of pi over 4, because this is a lot of work. All over 1 minus tangent tangent, which is tangent pi over 6. Tangent pi over 4. Guys, don't get it wrong plugging it in. I see it so many times. You just quickly look at your thing and you plug it in incorrectly. Double check to make sure you plugged it in correctly. All right, you already told me that tangent of pi over 6 is square root of 3 over 3. Plus tangent of pi over 4 is 1. On the bottom, I have 1 minus square root of 3 over 3 times 1. What's square root of 3 over 3 times 1? It's just square root of 3 over 3, right? So I didn't even need to write that if I didn't want to. It doesn't change anything. Okay.
Where'd you get the 1 minus?
I just stole it from here.
I know, but where'd you get that to put it underneath? What are you using? Okay.
I just copied it. I copied it from my brain.
It's kind of like what I did.
You can, yeah. Okay, now we know right here, if you guys look right here, these are most of the points. Was that hard to do? That is most of the points. The unfortunate thing with tangent, to get that extra point, so if this was out of 4 points, to get that extra point, you have to understand that this is not simplified, which means you need to get rid of the square root, which means you need to multiply by a conjugate, which means I need to multiply the bottom by 1 plus square root of 3 over 3. I don't want to do that. That seems difficult with fractions. So the first thing I'm going to do is I'm going to clear the fractions. This is that little tip that I told you, I don't know, a couple weeks ago that's going to keep showing up. If I need to get rid of a fraction, I can always multiply by the denominator. So if I need to clear a fraction, I can always get rid of it by multiplying by the denominator. So if I don't want a fraction in the denominator, I'm going to multiply everything by 3. But if I multiply everything in the bottom by 3, I have to multiply everything in the top by 3. But it turns out I wanted to do that anyway, because this will clear out this fraction. So now when I distribute, I'll have 3 square root of 3 over 3, which is just square root of 3. So that's just square root of 3. 3 times 1, that's just plus 3, bless you. On the bottom, I have 3 times 1, which is 3 again. And we're going to have minus, well, 3 times square root of 3 over 3 is just square root of 3. Now it's going to be easier to multiply by the conjugate. Can we all pay attention real quick? The conjugate has to be of the denominator. Of the denominator, because I want to get rid of this square root of 3. I want to get rid of the denominator, so I need to multiply the bottom by 3 plus square root of 3. I don't really look at it as a conjugate. I look at it as creating that difference of squares. Because now I have a minus b times a plus b, which equals a squared minus b squared, which means I can just square both those things. But what I do to the bottom, I have to do to the top. The bottom should be easy. I'm going to come all the way down here. The bottom should be easy because it's just a squared minus b squared. A squared would be 3 squared minus my b value is that square root of 3 squared. The biggest algebra block is multiplying a binomial times a binomial correctly with all the negative signs and stuff that can occur here. This one's kind of nice because I don't have a negative sign. So just remember, my style is take the square root of 3 and distribute it to both of these numbers. So I'm picturing square root of 3 times 3 equals 3 square root of 3. Square root of 3 times square root of 3 equals 3. You can look at it as square root of 3 times square root of 3 is square root of 9, which equals 3. So it does equal 3. I don't care if you look at it as 3 or square root of 9. It's up to you how you kind of do it mentally. All right, now I switch over to the 3. So I have 3 times 3, which is going to be 9. Yeah, Kate?
I'm confused where you got the 3 squared minus
Yeah, this is
3 squared on the denominator.
Where are we looking here? I just multiplied everything by 3.
Right, okay.
I multiplied by 3 to get rid of this fraction.
Yeah, I'm following you there.
Okay.
I just...
So are you okay with 3 minus square root of...
I was looking at that step in the back left as it was coming from there.
Oh, no, it was coming from I did this multiplication.
Gotcha.
Yeah, I did the multiplication. Okay, so now I have 3 times 3, which is 9, and then 3 times square root of 3, which is 3 square root of 3. All right, let's keep plugging along. I'm going to do the two constants first. 3 plus 9 is 12. 3 square root of 3 plus 3 square root of 3 is 6 square root of 3. All over in the denominator, 3 squared is 9. Minus square root of 3 squared is 3. And so the bottom is just 6. And now because in the numerator is being added or subtracted, I can break it apart into two fractions. I can break it apart into 12 over 6 plus 6 square root of 3 divided by 6, which equals 2 plus square root of 3.
Is it 6 root 3?
What was it?
Is that 6 root 3?
It's 6 root 3, yep. I just did it because it's 3 root 3 plus 3 root 3 would give me that 6 root
I don't know
3.
if that was like a capital G. Or
Oh, yep, I could see that.
I was-
That's a tough one.
It's the toughest one you'll get on these.
Yeah, that's a toughie.
But it is just algebra.
Oh.
It is just algebra. In fact, I would venture to say that this is algebra 1. For the most part. At least you learned it in algebra 1. Yeah.
For this one, I feel like I got the answer like a lot faster by multiplying by 3 after I just got an answer and everything. Like I didn't multiply by 3 when you did. I did it by 10.
So you multiply the top and bottom by 1 plus square root of 3 over 3?
Yes.
Okay, that's doable. It just creates a lot of fractions and people don't like...
There were fractions. I had like 1/3.
Yep. And people don't generally like fractions. I don't mind them. If you like doing it that way, awesome.
Okay.
Wait,
Okay.
What did you multiply by?
So what he did is he didn't multiply by 3. He said, I'm just going to keep the fractions until I don't need them anymore. So he multiplied the top and bottom by 1 plus square root of 3 over 3. So at this stage here, we just need to get rid of the square root. Let's go back in time real quick. So we could have, at this stage here, we could have multiplied by the conjugate 1 plus square root of 3 over 3 and 1 plus square root of 3 over 3. That will technically get you the right answer, but it creates a lot of weird fractions.
Okay.
So I'm not even going down that path. If you can go down that path, awesome. I'm going down this path. I'm going to say I don't like fractions within fractions, so I'm going to clear them by multiplying by a denominator.
The way you did it there was a lot more straightforward.
Yes.
You just following the steps.
Yes. But if I was to do it on my own, maybe I'd multiply by 3, or maybe I'd just do depends how I felt at that time. Because I can do fractions, but some people just don't like fractions, which I just teach you how to get rid of fractions. Okay, other questions? Yeah.
Actually, never mind.
Is it the same kind of question?
I had a question about, you kind of figured it out.
Yeah. Because there's 2 tangent ones that basically do the same thing. Other questions? Going once. Going twice. 3 times, because I saw people, hopefully you got them answered. Okay, then let us do today's lesson, which is I'm doing one problem, you're doing the other problem, and then we start our homework. So if you did your homework for this one, this is going to be a really easy lesson for you. In fact, if you look at the homework, it looks very much like last night's homework, just a little more practice. All right, I have to find the cosine of negative 7 pi over 12, but I picked this one in particular. Let's stop for a second. So yes, it's a negative, so I can use subtraction to make a negative, right? I can do a negative angle minus another angle, I have a negative angle. Let's be smart about this, though. Let's change it to a plus. And if you don't know what I'm talking about, look at your odd, even identities on your identity sheet. They're in that bottom left-hand corner. If you look there, it says cosine of a negative angle equals cosine of that same angle with a positive sign in front of it. So if that's an identity, I can do that anytime. So anytime I have cosine of negative 7 pi over 12, I can say, you know what? It'll probably be easier if I just do cosine of a positive 7 pi over 12. Because I'm allowed to do that. That's what the identity says. So now I don't have to deal with the negative. Now real quick, let's go to the tangent one. For the tangent one, can I just change that to a positive sign? No. What would I have to do? I would have to pull that negative out front, which is surprisingly not as easy as it sounds because you'd have to distribute that negative to everything. So a lot of times for tangent, I'm just going to leave that negative there. But for cosine, every time I see cosine of a negative angle, I'm going to just make it positive. Just makes our life easier. And now we have cosine of 7 pi over 12. How can I rewrite cosine of 7 pi over 12 so it's on my unit circle? Because 7 pi over 12 is not on that unit circle. And don't just shout it out. Try to come up with it on your own. How can I rewrite 7 pi over 12? I think I skipped a section too, didn't I? I'll go back to it. How can I write 7 pi over 12 as something that's on my unit circle? And how about everyone gives it a shot so you're just not waiting on someone else to do it for you? Unless they're going to take the test for you, then you can wait.
That would be cheating.
It would be. It's cheating in class too. It's cheating yourself by just waiting for someone else to give you the answer. Anyone think they found one? Weston? Pi over 3 plus pi over 4. Do we agree with that?
Yes.
I agree with that. Because pi over 3 is going to be 4 pi over 12. Plus 3 pi over 12, that would be 7 pi over 12. Okay, we're good. Now we go to our identity sheet and realize that cosine is the weird one. If I'm adding angles, it actually turns into subtraction. So if you look at your identity sheet, you should see that it's cosine, cosine, minus sine, sine. Cosine, cosine, minus sine, sine. Do you agree with that? Or did I say that wrong?
I agree.
Do we agree with that? Okay. So we're going to go, okay, that's cosine of the first angle times cosine of the second angle minus sine of the first angle times sine of the second angle.
Is this because it's the difference?
Because it's the difference. Well, it's not the difference. So be clear, Cade. I am adding angles.
Oh, okay.
But if you look at your formula for cosine, when you add angles, you actually turn it to a subtraction sign. It's not a mistake on there. That's exactly what you do. It's the one that's going to trip everyone up.
Gotcha.
Okay? So it's not a difference of angles. Actually, in the sum of angles, we turn it into a difference. We don't have time to go through the proofs, nor would you guys be that interested in the proofs, probably. All right, so now we have cosine of pi over 3. Cosine of pi over 3, that's either 1/2 or it's square root of 3 over 2. It is 1/2. Pi over 4 should be easy at this stage. That's just square root of 2 over 2. Minus, well, if cosine was 1/2, then sine must be square root of 3 over 2. And my sine of pi over 4 is square root of 2 over 2. Now we just multiply numerators and denominators. 1 times square root of 2 is square root of 2. 2 times 2 is 4. Minus square root of 3 times square root of 2 is square root of 6. 2 times 2 is 4. They have common denominators, so we can write this as square root of 2 minus square root of 6 all over the old quattro. Preguntas. Oh, questions. Go.
So I forgot, I like worked on this and I didn't, like, what should I say? I didn't like flip it and make it addition, and I still got the same answer.
You would get the same answer. You have to get the same answer. So Charlie, if I would solve this as negative 7 pi over 12, I should get the exact same answer as this one.
So you're just moving the negatives in different areas. But
I'm just putting negatives, and it comes out the exact same, right?
yeah.
Yep. That's why I'm allowed to make this. Charlie, if I came up with a different answer, it meant I made a mistake in the beginning. I couldn't do this. But because I can do this, we should come up with the exact same answer.
So on the one for the bell work, if we just, is the sine of negative 75 degrees, would that be, like, is that kind of the same thing as, like, would that end
Kind
up-
of, but sine, you'd have to pull the negative out front. You'd have to find the negative sine of 75 degrees. Okay, let's go back in time real quick because I think I skipped some problems. We're supposed to express each of these angles as an addition or subtraction where we know the angles. 15 degrees, is that on a unit circle? No. So if it's in a section that says you cannot use a calculator, you have to know that I want you to add or subtract angles. So instead of 15 degrees, what can I rewrite 15 degrees as in terms of angles that I actually know the values of? Yeah. 45 minus 30 would work. Would anything else work? 60 minus 45 would also work. So all those equal 15. Okay, 195. Is there a way to get to 195 and I know both of those angles are on my unit circle?
150 plus 45.
150 plus 45?
Are we not actually doing anything with these?
Nope. Is there another way?
225 minus 30.
225 minus 30. What if I needed negative 5 pi over 12? I couldn't make it positive. How could I make negative 5 pi over 12 with angles that I know? Pi over 3 minus 3 pi over 4.
That's 60 minus 1 in degrees.
Let's just stick with the radians because we're in radians. Let's double check this. So pi over 3 would be 4 pi over 12. And then our other one would be 3 pi over 4 would be 9 pi over 12. Yeah. Any other way? With maybe smaller angles? We can make them both negative angles.
3 pi over 12 minus 2 over 12.
Say that again.
3 pi over 12 minus 2 pi over 12.
Minus 2 pi over 12, so pi over 2.
Yeah. 2 pi over 6.
You're saying it's pi over 6?
Which is negative, which is 2 pi over 12. Right?
Yeah.
If we made it negative, then
So go a negative pi over 6,
yes.
and then do it with a negative pi over 6. So pi over 6 equals 2 pi over 12.
over 6 and negative 3 pi over 12, which is negative pi over 4.
So minus pi over 4.
Yes.
So pi over 4 equals 3 pi over 12. So we make them both negative, right?
Yes.
I wanted that one. I wanted that one. And why I want this one is because this one has a negative angle in it. In this case, I would have my angle A would be negative pi over 6. My angle B would be a positive pi over 4, where the negative tells you your identity. So this is the rare case where I'm actually going to throw negative angles into the problem. So Grant, that's why I wanted to get to this one, because it's important to understand when to plug negatives in and when not to. In this case, we have a negative way out front, so I'm going to use negative pi over 6. I will not use negative pi over 4 because the negative is part of what identity I'm going to use. So this is the rare case where I actually put negative angles in. Most of the time we put positive angles in. So if you're not sure, just put positive angles in because more often than not it'll be correct. So this is that weird case that we would have to put negatives in. All right, let's go back to this problem. Tangent of negative 15, let's leave it as negative 15. Can someone come up with a way to get negative 15 out? Yeah.
Can you do 30 minus 45?
I could do 30 minus 45 degrees. Can someone give me another way to do it?
45, 120 minus 135.
Say the one with 60.
45 minus 60 degrees.
Tangent of 45 minus 60. And we know there's other ones, right? I'm going to stop here because one of these is difficult, the other one's easier to work with. Surprisingly, they'll both end up with the same answer. No matter which one of these pick, you'll come up with the same answer. Just one's more difficult than the other. And the way I'm going to decide which one's more complicated is, what's the tangent of 30 degrees? Square root of 3 over 3. What's the tangent of 60 degrees? Which one sounds easier to work with? Square root of 3 over 3 or just square root of 3? Square root of 3. So in this case, if I went one extra step, I'm going to find out that this one's actually easier to work with. They'll both get you the same answer, but one has square root of 3 over 3 and one just has square root of 3 in it. Pick either one you want to work with and solve this one. When you are done with it, I will check it off that you know how to do it, and you can work on your homework. If you're not sure what to do, ask questions. Tangents are the hardest ones that are on here. Yeah?
I already started this.
Oh, cool.
I started with